Hi, everyone. Welcome to Chapter 8 on non-renewable energy sources. In our last chapter on climate, we talked a bit about how the burning of fossil fuels is implicated in the climate changes that the Earth is undergoing, but we haven't actually talked in much detail about what fossil fuels are. So that's what this chapter is largely dedicated to doing. Our learning outcome includes describing how chemical bonds are used in combustion to derive energy, listing specific examples of non renewable energy sources, explaining what makes an energy source non renewable, describing the main types of fossil fuels and how they are formed, explaining the environmental impact associated with exploration, extraction, and use of the different types of fossil fuels. And lastly, explain nuclear energy, how it works, its benefits, and its risks. We're going to begin at the beginning by describing how chemical bonds are used in combustion to derive energy. And to tackle this, we need to briefly step back and review some concepts that we learned back in Chapter 2. In Chapter 2, one of the things that we learn is that there are two different forms of energy in the universe: potential energy, which is latent energy that is being stored, and then kinetic energy, which is energy that is active, or in other words, in motion. And when we are talking about potential energy that is stored in chemicals, because that's what fossil fuels are, they're chemicals. Remember that the chemical potential energy is stored in the bonds between atoms within a molecule. That is to say, it's stored in the electrons that they are either sharing or have transferred between one atom to another, and then releasing that energy. That involves breaking those bonds and moving those electrons and their associated energy around. So that's a quick overview of what we learned before. Now we're going to build on that by introducing another idea, which is that not all molecules store the same amount of energy. And part of that is because not all chemical bonds are equal in terms of how much energy they store. Chemical bonds that are stronger contain higher amounts of energy than chemical bonds that are weaker. That probably makes sense to us intuitively. But what makes a bond strong or weak is ultimately the length of the bond, meaning the distance between the two atoms being bonded. The shorter the bond between two atoms in a molecule, the stronger it is. And this should make sense to us intuitively as well. Especially if you've ever played around with magnets before, what you may have noticed is that you move the magnets closer together, the attraction becomes stronger, and it's harder to pull them apart. Now, magnetic energy is different from chemical energy, but the principle is the same. The shorter the distance between the two attracted objects, the stronger the attraction. The shorter the bond length, the stronger the bond. And within molecules, there are several factors that influence how long the bond is, including the size of the atom, the number of electrons, and the distance of the orbitals from the nucleus. We can look at a specific example comparing the length of bonds between carbon and hydrogen, carbon and oxygen, and carbon and carbon. Of these three bonds, when carbon bonds to hydrogen, the length of the bond is 110 picometers. When it bonds to oxygen, the length is 143 picometers. And when it bonds to another carbon, the length is 154 picometers. So, the first bond, the one between carbon and hydrogen, is the shortest and therefore the strongest. And the reason why it is the shortest is because hydrogen is a very small element, the smallest of all of the elements, in fact. It only has one electron, and its orbital is very close to its nucleus. So things aren't as crowded in the bond, and the two atoms can get closer together compared to carbon and carbon bonds. Why does this matter, and what does it have to do with fossil fuels? Well, when fossil fuels are used for energy, they undergo combustion. Combustion is a chemical reaction between a fuel and an oxidizing agent. The more familiar term for a combustion reaction is burning, and the fuel that is burned is a combustion reaction, which is usually a hydrocarbon, which is a carbon and hydrogen based molecule. Wood is composed of hydrocarbons. So the burning of wood, like you see in the photo, is a combustion reaction. Fossil fuels are also composed of hydrocarbons. To an even greater degree, fossil fuels are composed of molecules that are extremely rich in carbon hydrogen bonds. And as you can imagine, this also means that they are very energy dense because carbon hydrogen bonds are short in length, meaning they are strong, meaning they hold a lot of energy that can be released through the proper chemical reaction. The oxidizing agent involved in the combustion reaction is usually oxygen. This is why a fire can't burn without sufficient oxygen. And the product of the reaction are carbon dioxide, water vapor, and energy in the form of heat and light. If this sounds familiar, it should. A combustion reaction is essentially identical to the metabolic process that organisms use to extract energy from carbohydrates. Cellular respiration, which we also learned about previously, cells oxidize carbohydrates like glucose and break them down with the aid of oxygen, and in the process generate water, carbon dioxide, and energy that is useful for their cellular needs. So when you say you are burning calories, you are literally burning calories. The breakdown of carbohydrates within cells is a slow, controlled combustion reaction. But that's not the type of combustion reaction we're concerned with here. In this chapter, we are interested in the combustion of fossil fuels, which are chemicals with a high hydrocarbon content that are found in the Earth's crust, which were formed in the geologic past, specifically between 100 to 500 million years ago from prehistoric organisms, and can be burned easily to release energy. There are three main types. They fall under this definition, and that includes oil, natural gas, and coal. And in this chapter, we are going to be dedicating a section to each of these three types of fossil fuels. And in a moment, we're going to address in detail how each of them is formed. But to give you a broad overview, fossil fuels were formed from prehistoric organisms that died and then quickly became buried or submerged underwater. Being submerged or buried caused their decomposition rate to slow to an extremely slow pace. Again, we're having a lot less aerobic respiration in these conditions. And so the time it takes to break down these components is a lot slower. And they're compressed under the weight of the material under which they are buried. And this leads to conditions that cause them to transform into what they are today. Now, we humans use them as energy sources in two different ways. As a primary energy source, fossil fuels are used directly in their current form without transforming them into another type of energy. So, burning coal for heating or cooking, or burning gasoline, which is an oil derivative, for transportation are all examples of primary energy usage. Fossil fuels can also be used to generate secondary energy, which is where the fuel is burned to create another type of energy. Usually, that other type of energy is electricity, which has the advantages of being easily transported over long distances and is usually useful for a wider variety of purposes. To give you a sense of how big a role fossil fuels plays in our primary and secondary energy in the US, 80% of primary energy in the US is sourced from fossil fuels. You can see that reflected in the graph here, which runs through the year 2021. Only the green and orange sectors, which represent renewables and nuclear energy, respectively, are non fossil fuels. Everything else, the red being petroleum, which is oil, the light blue being natural gas, and the dark blue being coal, is all fossil fuels. You can see how coal has tapered off in recent decades, but it has pretty much just been replaced by natural gas. As far as primary energy use by sector, the highest use comes from the transportation sector, then the industrial sector, followed by residential, and then lastly commercial. When it comes to secondary energy usage, About 60% of the electricity in the US is also sourced from fossil fuel. So a better ratio than primary energy, but still reflecting a deep dependence on fossil fuels. And this is concerning not only because of their role in driving climate change, but because fossil fuels are a non renewable resource. Non renewable resources are resources that have a finite supply. There's not an infinite amount of them and cannot be replenished within a human timescale. And because fossil fuels require millions of years to form, they truly cannot be replenished with a human timescale. Remember that humans have existed for less than 200,000 years. We've only been around from the Holocene and part of the Pleistocene, which I've boxed at the top of the timeline in yellow. On the other hand, most coal deposits were set during the Carboniferous period, which occurred between 360 to 300 million years ago. And I've boxed in red on the timeline for that as well. Even the youngest fossil fuels that we know of are about 65 million years old, and the oldest are over 500 million years old. There are likely some fossil fuels in the process of forming right now, but we have to wait dozens or hundreds of millions more years for them to cook, and that's not a realistic human timescale. So these fuels are non-renewable. Once they are gone, they are gone, and humans are using a lot of them. But our main discussion on how humans use the three main major fossil fuels and the consequences of that use are going to come in later sections of this chapter. For now, we are going to look at how the three major fossil fuel types are made. We said that the three major fossil fuels are oil, natural gas, and coal. And while they're all formed by the same very basic process, the type formed depends on which dead organisms it was formed from, how long it was buried, and the temperature and pressure conditions during the time of its formation. We're first going to look at oil and natural gas, and then we'll turn to coal before closing out the section. The first step in the formation of oil and natural gas is called deposition. The root word here is deposit. Basically, this describes the depositing of dead organisms that become the fossil fuel. For oil and natural gas, this process happens in water, mainly the ocean. Marine organisms, mostly phytoplankton, die and then settle to the ocean floor. At the bottom of the ocean, there is very little oxygen available because it's so deep and distant from the interface with the atmosphere. And so, there at the bottom, where there's no oxygen, the phytoplankton will start to decay very slowly under anaerobic conditions. And this is happening. The second stage occurs called diagenesis. During diagenesis, marine sediment becomes buried under new sediment layers that form on top of it. And as this happens, the decaying phytoplankton become compacted. As a result of this compaction, water and oxygen get forced out of the sediment, and a material called kerogen is formed from the partially decayed marine organisms. Kerogen consists of waxy chemicals that are a precursor to oil and gas. Then next comes maturation. As more sediment layers build up, the kerogen gets buried even further and the pressure level increases, as does the temperature. Under these high temperature and pressure conditions, the kerogen undergoes thermal degradation, which is also known as cracking, and this transforms it into hydrocarbons. The higher the pressure and temperature, the smaller and lighter the hydrocarbon molecules. Therefore, more shallow regions with lighter pressure form larger, heavier molecules that become oil, and deeper regions with higher pressure form smaller, lighter molecules that become natural gas. The final step is called trapping, which is where oil and gas seep up through the layers of the Earth's crust until hitting cap rocks, which are rocks that are dense enough to where the oil and gas can't seep through them, and so they are blocked from reaching the surface and are trapped underground. And because gases have lower density than liquids, the natural gas will accumulate at the top of these trapped pockets in what's called a gas cap. and then the liquid oil deposits will be found below it. So that covers the formation of oil and natural gas. The third type of fossil fuel is coal, which undergoes a very similar series of steps to oil and natural gas, with the main difference being that the formation of oil and natural gas happened in bodies of water, while the formation of coal happens on land. The deposition of coal occurs when terrestrial organisms, including ferns, shrubs, vines, and trees, die and accumulate in wetlands, along with algae that grow in those wetlands. Then the dead organisms become buried or submerged in the wetlands, where there is little oxygen available to aid their decomposition. And so slow, anaerobic decay takes place. And over thousands of years, layers of partially decayed plant matter will accumulate. The term for those layers of partially decayed plant matter is called peat. So therefore, this step is called peatification. And then the next step is called coalification, which is where the peat becomes further buried by accumulating layers, and the pressure and temperature increases among the peat layers, which forces out water and leads to the formation of a material called lignite, which is the intermediate between peat and true coal. Lignite is considered to be the lowest quality of coal because it is high in moisture and contaminants. The formation of black coal takes additional time, with more buildup of layers that increase temperature and pressure, which forces out the moisture and contaminants and leads to the creation of the material that we recognize as coal. In our next section, we're going to be looking more at coal, including how it is mined, how it is used, and the consequences of burning it as a fuel.